This is an interesting question because for the first time in our videos we are going to be doing the volume of a solid revolution about a diagonal line as opposed to a horizontal or a vertical line. What we're going to do is we're going to do three methods. The first one is probably the easiest. The last one is just added because it's interesting, but it's probably not the best way of doing it. Okay, so let's have a look. Let's go straight into method one. So obviously, clearly here we have y equals x, and here we have y equals root x, and we are revolving it around. So what we are going to do in the end is we're going to have something along the lines of that, and we're going to revolve it around, and we're going to integrate from here up to here. Okay, but I'll tell you what, let's draw the diagram a little bit again, because that was just for the thumbnail, just to impress everybody. I'm sure no one was impressed. So here's the y equals root x. Here's y equals, so here's y equals x. This is y equals root x. So clearly this point here is 1, 1. This is obviously the origin. And what we're going to do is we are going to draw this point here. And obviously now that is ds. It's a small distance along the line y equals x. And let's call this distance here height. And so clearly, just generally speaking, using the disk method, the volume of revolution of this around y equals x is going to be pi the integral of h squared ds. That's the general, but we need to do a little bit of a jiggery-pokery in order to get that into a format that we can do. So first of all, let's have a look at this little triangle here, which is a triangle where we have here ds and we have here dx, a small amount along the x-axis, and here dy. Now clearly, as this line is y equals x, we know this angle here is pi over 4, so we know that angle there is also pi over 4, and therefore we have that dx ds equals cos of pi over 4, which equals 1 over root 2. Therefore we have that ds is root 2 dx, and that's how we're going to convert our ds here into dx. Now let's have a look at this bit here. So we got here, we've got h, and then we've got a right angle triangle here, which is that bit, and we need to find this bit here, which is this, and that of course again is pi over 4 by symmetry because it's a now this point here is going to be, if this is x here, well, as it's y equals root x, this point here is going to be x root x, and this point here is going to be x. So this distance here is going to be root x minus x, and so therefore again by using basic trigonometry we are going to have that h over root x minus x is equal to cos of pi over 4, which is 1 over root 2, and therefore we have that h is equal to root x minus x over root 2. So now we have h in terms of x, we have ds in terms of x, so now we can do our general integral all in terms of x. So therefore let's just have a look here. So we have that basically pi the integral of h squared ds, which was our general disk formula, becomes pi the integral, well, let's have a look what we're integrating across. As we're integrating dx, we're integrating between x equals 0 and x equals 1, because that's the point 1, 1. So it'll be pi the integral between 0 and 1 of, okay, h squared, which we've already established is root x minus x over root 2 squared, times by ds, and ds is root 2 dx, that's root 2 dx, and now we have a very simple integral to perform here. That equals pi over root 2, the integral between 1 and 0 of root x minus x squared dx, which equals pi over root 2, the integral between 0 and 1 of x minus 2 x root x add x squared dx, and that equals, just a bit more space here, pi over root 2 x squared over 2 minus 4x to the 5 over 2 over 5 add x cubed over 3 between 1 and 0, which equals pi over root 2 a half minus 4/5 add a third, which equals pi over 30 root 2. And that is our volume of revolution around the point y equals x. That is the answer, and that's how we do it using method 1. Okay, now method 2, if we just remember that point there, by the way, because method 2 we end up getting exactly the same integral, and I won't bother going through the whole thing again. Once we got to that integral there, we know the answer is pi over 30 root 2. But okay, here's method 2. What we're going to do, instead of converting ds into dx, we're going to integrate directly ds. So let's just have a quick drawing of this diagram again. So here we got y equals x, and here we got y equals root x. So this point here again is the point 1, 1. Here we have our origin 0, 0. Here is ds, and again here we have h. This point here, what we're going to do is we're going to parameterize it. We're going to use x equals t and y equals t for t between 0 and 1, and that basically is the line y equals x. That's the parameterization that we're going to use. And so therefore this point, as this line here is y equals root x, then this point here is going to be t root t, and this point here is going to be t. Okay, now I think I've got everything there. And so basically what we have now is, because we're using parameterization, what we can use now is we can say that ds dt is equal to the square root of dx dt squared add dy dt squared. This is basically a line integral. And dx dt, well, dx dt is just going to be 1, and dy dt is going to be 1. So therefore we have that ds dt is going to be equal to root 2. Now h, which is that distance there, by exactly the same logic that we had before, h is going to be equal to root t minus t over root 2. Exactly the same as before, using exactly the same triangle up there. Okay, so now what we can do is we can say that our integral is the integral pi times s goes from 0 to root 2, because obviously if this is 1 and this is 1, then the distance s is going to go here is root 2 of h squared ds. That becomes pi times the integral t equals 0 to t equals 1 of root t minus t squared over root 2 squared times ds dt times dt, and we know ds dt is root 2, so that equals pi over root 2, the integral between 0 and 1 of root t minus t squared dt, and that is exactly the same integral that we had up here, so we don't need to bother doing it. It's going to give us the answer, what was it, pi over 30 root 2. So it's basically the same way that we're doing it. It's just this way we're not converting to dx, we're keeping it as ds and actually parameterizing it. Now method 3 is quite interesting, because what we're going to do in method 3, so it's the same question here, what we're going to do in method 3, again let's just draw it very quickly. There's y equals x. We're going to use parameterization again. There is y equals root x. Okay, and we're going to, let's say this point here is tt, and this point here therefore is t root t. Use the same parameterization. But what we're going to do is we are going to rotate everything 45 degrees, or pi over 4, clockwise, so that we basically end up with this, which is the standard disk method volume of rotation, which everybody can do relatively easy. And the way we're going to rotate by 45 degrees clockwise is we're going to use the matrix cos theta minus sine theta, cos theta. That basically rotates by theta anti-clockwise. So we just got to be a little bit careful with our signs. Here's our all stations to crew here. We are rotating clockwise, and so therefore our matrix will be cos of minus pi over 4 minus sine of minus pi over 4, sine of minus pi over 4, and cos of minus pi over 4. Just got to be a bit careful with that, which equals 1 over root 2, because cos of minus is the same as the cos of plus, 1 over root 2, because even though sine is negative, we have negative there, minus 1 over root 2, 1 over root 2. So this is the rotation matrix that we are going to have to apply. And basically, if we look at this y equals x, that is just going to turn into the x-axis, so that's easy, we don't have to worry about that. What we need to worry about is y equals root x is going to turn into this one. What is the parameterization of that? And the way we find that is by putting the parameters t, root t, through that matrix, and that will give us the new parameters of this curve here, which we then just rotate around the x-axis and use the standard disk method. Okay, so basically what we have there, I hope that was clear, we have 1 over root 2, minus 1 over root 2, 1 over root 2, 1 over root 2, times by t root t, and that gives us our new parameterization, t over root 2, add root t over root 2, minus t over root 2, add root t over root 2. And if you don't know how to multiply the matrix here, just go and check one of our other videos on Introduction to Matrices. So this now is the new parameterization of this curve here. So basically all we need to do now, let's just get a bit more space. We have this curve here, which is this parameterization here. Of course, all we need to do here is h, and there is dx, and we're going to integrate along there the disk method, rotating that around there. So that becomes basically pi the integral of h squared dx. Okay, but what we're going to do is we're going to stick everything in terms of t, so that becomes equal to pi, the integral between t equals 0 and t equals 1, remember the parameterization is still the same, h squared, okay, well h is basically just y, which is this one, the parameterization of the new curve, so that is minus t over root 2 add root t over root 2 squared, times by, well dx, what we can do, as we're doing it in terms of t, we're going to dx over t times dt, so we need dx dt. Well, x is this is x, so therefore dx dt is equal to 1 over root 2 add 1 over 2 root 2 root t. All I've done is I've differentiated the x parameter there. And so now finally we can put everything together, and our solid of revolution is going to be equal to pi. We can take the root 2 out squared, so that'd be pi over 2, the integral between t equals 0 and 1 of t squared, just multiplying this square out here, minus 2t root t add t, times by dx dt, we can stick dx dt in here, 1 over root 2, 1 add 1 over 2 root t dt. And we have here a slightly time consuming but relatively straightforward integral in t, and this is the volume of the solid of revolution, okay, which equals pi over, we can take the root 2 out as well, pi over 2 root 2, the integral between 0 and 1 of, let's just multiply all this out, t squared minus 2t to the 3 over 2 add t add t to the 3 over 2 minus t add root t over 2 dt, and that equals pi over 2 root 2, the integral between 1 and 0, well obviously that cancels with that, that leaves us with t squared minus 3 t to the 3 over 2 add root t over 2, and finally we can do our integration now, and that equals pi over 2 root 2 t cubed over 3 add 3t to the 5 over 2 over 5, minus, my apologies, minus add t to the 3 over 2 over 3, all between 1 and 0, whoops, I've run out of space here, which equals pi over 2 root 2 a third minus 3/5 add a third, which equals pi over 2 root 2 2/3 minus 3/5 which equals pi over 30 root 2, which is the same answer we got using the other two methods. Okay, now this third method is quite interesting because it teaches you how to rotate a curve clockwise around whatever, using a matrix and using parameterization. So this one is, the third method is probably the best method for really beginning to understand how to use parameters, how to use matrices, how to rotate stuff around, but probably the best way of doing if you were in an exam, for example. I certainly wouldn't use the third method if you're in an exam. I would be tempted to use this first method here, where you're basically just using in terms of dx, and that's probably the easiest. Okay, I hope you found this instructive and useful. If you have, please like this video and subscribe to the Gresty Academy YouTube channel.